Okay, today I will show you, let's say, a complete modeling and solution part uh, with our task. And here, this is a model I just generated. And of course, it's actually not with the required size of the pipe. You see, in this case, it seems the thickness is too much. I just use some random value just to give you an idea how we do it. So I will show you completely start from the beginning. Okay, I will click everything. And this is the same as if you type finish and with a slash and clear. Okay, this is the same. They will ask you if you want to clear. It will destroy everything. Yes, this is the same thing. Then we can start, of course, from preprocessor element type first. Add, and solid 185. Okay. I think you are more familiar with this kind of step now. And the material, we have to go to structural linear elastic, isotropic, and there will be a Young's modulus and Poisson ratio. The Young's modulus normally for steel, it varies from 2 to 2.1 times 10 to the power of 11. Okay, and we can add also a density for steel. And then there will be a nonlinear part in elastic and rate independent. And this is plasticity and multilinear. And here, let's say it has to be like 1, 2, and add point, let's say 3, 4. Again, I'm using like random values, and this is not the one you need. You have to identify what are these values. But this is like one way we can do. And pay attention there, this ratio between these 2 and 1 has to be exactly equal to the Young's modulus. You just input like 2 something times 10 to the power of 11. If they are not matched, there will be no problem during the modeling, but when you start to solve your model, there will be an error there to say these values are not equal. So the program stops. So pay attention to this one. Okay. Now I have this one. If I make a graph of it, you will see we have this multilinear part, okay, with several data. And here the linear part, because this is the elastic part. So the ratio here, or let's say the gradient or slope of this straight line has to be equal to, the gradient has to be equal to, let's say delta y over delta x. Okay, forgive my writing. It has to be exactly the Young's modulus. Okay, this is important. If this is defined, we can go to define the thickness. No, for solid we don't do that because we do it in the modeling. For if we have a shell element, you have to define the thickness of the section. So now we can start to create our model. We can go to the volume and hollow cylinder, or maybe partial cylinder. So as I said before, we could have 4 in the left part, 3 in the middle, and 4 on the right part. This is a solution to what Mateusz had that problem, because let's say for this, if this is the left part, okay, we're going to do, we have this kind of tube. So this is one volume. How we divide it into 4, we can have one layer in the thickness part, and with this one, this small one, equals the depth of the corrosion. Then you can have this one equals to the width of the corrosion. So here in this case, basically you can have 1, 2, and 3, 4, let's say 4 volumes for the left part and the right part. For the middle part, you just have 2, 3, 4 without the 1 because that is where the corrosion defect occurs. Okay, hope I made it clear. So how to do this modeling? We can skip this WP because they will be 0, 0. You say they can be the origin, or you can simply ignore this one. They will be the same as 0. So the outer radius, let's say if you are having a 10 and probably a, let's say 9 here, okay? The order doesn't matter. It doesn't need to be like increasing or decreasing order. They both okay. If you put 9 or 10 or 10 or 9 there, they can accept with the same thing. So this degree, let's say negative 20 to positive 20. The depth will be the length. If I have a radius of 10, probably the length will be 10 times this value, or 20, because this is the radius. So 10 times the diameter is 20 times. So the length will be about 200. Then here I use 100 because I'm going to model half, a little bit less than half part, only the left part. So when I click apply and use the fit view, okay, I have it there. But of course you have to remember the value you used, 10, 9. So I'm going to do a 22. You can do a arithmetic operation there. So even you can count by mental math, probably this is 340. This is the same as negative 20. But you can type like a subtraction operation there. 360 over minus 20 is no problem. Depth will be the same as, what is the value I used? 100. Okay, apply again and fit view. Now you have these two cylinders. And of course you can do again, before we have 10 to 9, let's assume this 9 is the 10 to 9 is the corroded part. So we will start have 9 to, let's say 8. Okay, so we do the same. 2, let me check. So apply, okay, you have this inner, let's say inner layer. Then it needs to be 8 to 9 to 8, 20, 340, and 100. Apply. So normally you can check, use this isometric view or this oblique view. Okay, you have this left part of the tube. So you can do the same thing to the middle part, but in this case you have to move because now we have this. You see WP, WX. This is the work plane, and you have your work plane at the starting section here, which is Z is 0. But now we are going to model new tubes like this. But with the depths, you can have only, you don't have like Z1 to Z2. You have only a Z, the length. So we have to move the starting point here, Z, the new Z0, let's say. So in this way, we have to offset the WP, the work plane, to XYZ locations. So we have to move to this point, 0 and 0. Now this is referring to the global Cartesian coordinate system. So if you remember, the Z is 100 here. So, okay. Since it's not okay. me check what is the problem. So let's move it to global origin first. It's there. We have to offset it to XYZ location. 0, 0, 100. Or maybe with this WP coordinates. 0, 0, 100. Okay. No. So I move it back to what I want is to move it here. Okay, XYZ here. And see what's the problem. By XYZ locations or align with, or maybe this one, align WP with XYZ locations. Okay, I'll put 0, 0, 100. Okay. Yeah. Yes, it's supposed to be like this. Okay, I don't know what was the problem before. But now we successfully moved it here. If you could see on the screen, we have this one there. So now we can follow the same step. We can do, now we do the inner part first, from 8 to 9 with negative 20 to 20. Let's say we will have a shorter one for the corrosion length. Let's say is a 10. Okay, then if we rotate your model, you will see we have yes, this one. No, I think this XYZ was rotated a little bit. So I have to, in this case, I have to delete volume and below is better because there will be area and nodes and line, key points and lines there. So it's better you delete everything there. So there's a problem with, so I will move the WP back there. Can you see clearly if there's a rotational movement of it? I think seems okay. So now I offset it to 0, 0, and 100. Okay, seems okay. So now I will do that modeling again. Partial cylinder from 9 to 8, negative 20 to 20, and 10 here. Fine. And again, this is a problem. Is it? What? What is the problem? Okay, now we have to delete these lines, areas, a plots. It seems I didn't delete this area and below. So delete areas and below. Block everything there. Fine. And that area there. Okay. Yesterday when I tried, there's no problem like that. So yes, this WZ is rotated. Why? Offset WP to original global origin. So it has been rotated already. Assign with global partition. Okay, now it seems it's okay. I don't know what's happening. Probably I did something while doing this offset, and XYZ location I rotated a little bit. Now let's go back to the normal procedure. I move it, supposed to be here. Okay, now it seems if I'm using this view, yeah, it seems it's pretty much okay. Okay, now I'm going to create these volumes, partial cylinder from 9 to 8. This is the inner part. Negative 20 to 20 with a 10, then apply. And of course I will go with 9 to 8 with the majority of this 20 to 340 and with a 10. Okay, if I check in this view, I have this inner part. So for the outer part, we don't have this small corrosion part. Then this will be 10 to 9. And from 20 to 340 with a 10. Okay. So now this is the left part and the right part, sorry, the middle part. For the right part, there are different ways to do it. By the way, there's always different ways of modeling techniques. Depends just which one you like or which one you are better with. So for the right part, you can, of course, using this partial cylinder and to do 4 cylinders. But there's a better way actually here. You can just copy paste. You can copy volumes. In the selection of volumes, there is a box which is very good to be used. You can just hold on your left mouse button to select, to make a rectangle, and then you can select. Okay. Even you didn't see the volumes being selected, but it says count 4. See here? Because we have 4 here and 3 there. So that's why it said maximum you can select 7 because they are 7. And the minimum, at least you have to select 1. And the count 4 means 4 volumes being selected. So this is the 4 volumes we want from left part. So, okay. And then how many copies you want? If you want one more copy, this means 2 here. Okay, this is mean including the original one. So if you want to make 1 copy, and that is a 2 number here you have to use. And we are going to move it via Z offsets. XY we will keep it. Z it will be 100, but it's not only 100. Let's say we have this volume here, and the starting is this one, right? 0, and we have 100 here, 110 here. So the idea is to make it like this, right? So the distance we're moving is actually from here to here, okay? So that's why here we have to prove, we have to use 100 plus 10, let's say. Or as I said, this operation works, or you can just type 110, there's no problem. So keep the rest and okay. Oops. What was wrong? Okay, something is not okay. Then I have to delete the. I have to delete this. Delete the volumes and below. Okay. I think the problem is from this 100 plus 10. So maybe that doesn't work. So I have to copy volumes, use a box. I stack those 4 again. Okay, and here instead of 100, it seems they move like 100 to Z and 10 to the Y direction. So better to use just one number. And come on. Why it's like that? X, Y, Z offsets. If I type P here, it's by peak, and KSWP is supposed to be. Let me check this command of V delete. So the KSWP has to be 1 to delete everything. So it's P and this value, and 1 there. With a box, I delete this once. Okay, a plot, just to check if there are errors there. I have to delete areas. Yes, plot lines, L plot, and L delete. That is because we didn't do the volume in the below. And key points K plot. We have key points there. We have to delete these key points box. Okay, done. So now if we plot volume again, we have these volumes there. So let's select V cell P. I will use a box to pick these volumes. Okay. And the replot. Okay, we have only these 4. If we list the volumes, we have 1, 2, 3, 4, and we're going to do copy. Now we can pick all because we have only 4 being selected, and pick all is being copy everything being selected. So inactive coordinate system. So I think the problem is I move the coordinate system maybe. Let's change it to active coordinate system to global Cartesian. Yes, it is there. So copy everything with Z 110. should work. Okay, now it works. I think there is a problem when I try to move the working plane. I change a little bit the coordinate system. Now you see we have middle part and middle part missing. We have left and right. That is because the middle part was unselected. If we select everything, or we can simply use all S or cell and replot. With replot, you will see everything there. This is all the volumes. If you do vlist, you will see you have 11 volumes. This means 4, 3, 4. Okay, add up to 11. Then you can easily do a V glue, and you can do a with all, and it takes like a few seconds. Okay, there will be no problem doing this V glue. If you don't have that explains why I need to split, let's say, the outer part into 4. That is actually the purpose is to have a better V glue. Okay, if you have just a single one or you have 2 there, you don't have a common boundary line for this corrosion part. So during the V glue, there will be a problem. There will be some warning there. Okay, if we rotate our model, we will see how it looks. Okay, we can use this zoom model to see a better view of this corrosion part. Okay, and of course we can, this is the volume, we can plot the area, a plot, basically same thing, and L plot, we see we have this kind of lines, and of course we can plot the key point. Okay, there are not many, just a few. Okay, then next step is going to mesh it. Meshing. Before mesh 2, we can go to these attributes for all volumes. These values are by default setting, so we can simply click OK. I think since we have just one type for everything, like one type for material, one type for element. So if you forget this part and doing the mesh, I think there will be no problem. But it's important if you have like different types of material or different types of elements, then you have to say which is which. So probably you have to select. So the select function is quite well. You can select things by number pick or by location or attached to or etc. There are many different functions. It depends on which one is easier to be used. Okay, then you can select this specific part and then to give different attributes. Okay, now we can do the mesh tool. Of course, we can try to smart size. I will try here how it works. Mesh, I can pick all. This is what you showed me before. And but of course, if you have doubt how we can improve this meshing, that is, maybe we first clear all these meshes. Okay, clear everything. Then you can plot the volume again. They are there. Plot the lines. So now another way, instead of globally smart size, we can go to more manual controlled lines set. Okay, we want to set for some lines. So let's see it in this view. We can use this box. We select these lines, and we give a number of division there. Let's say 100 divisions for them. This spacing is used when we need to have like increasing a different mesh style. Like you can have increasing from 1 to 2 to 3 to 4. I mean the element size, like changing element size. You can use this spacing. which is not used in our case. So after clear OK, here you will see we have this dash line there. If we see it more detail, okay, this means they are predefined this division, number of division. So we can do the same thing with mesh tool. It's here. Set lines with a box. I think I will do this. Let's say the measure arcs. Okay, 12 being selected. As you see, you have 3 for each one, and you have 4 end section. So 12 is the correct answer. Apply. Let's say we give a 40 division there. Apply. Okay. The difference between apply and save, I included in the slide. Apply means you can have this still working there. But there's not big difference. If you use OK, then you just click it one more time. Then let's say what we do with this minor arcs. Okay, 12 again, apply. I will say I give a smaller value of 10, maybe 10, 8. Okay, apply. And we can move a little bit more there. Okay, so I will say box, maybe this, there will be 4 there. Okay, 4 being selected. You will have this one, the same 4. So you have 8. So let's say you divide it into 2 maybe. And then you can select those ones. As I said, I use a random value for like thickness or corrosion depth. So actually, of course, this is like half of the thickness being corroded. I don't know, in your case, maybe you have group dependent value, but maybe not that much. Then you can check if you use the same number of divisions for this corrosion part and the remaining part. Here I will do the same thing, okay, with 2. So just check all the lines, okay. We still have something not with dashed line. That is this middle part. Okay, so where is it? Set lines. So we select those ones. Okay, then we say we can use a number. I mean, the element size will be similar to this one, but smaller would be better, a little bit smaller, because they are the critical area. So I'm not sure, maybe I can give it 10. Okay, I think I want a bit more, 20. Okay, fine. So let me just check everything. If I have all these lines defined, I think so. So now mesh tool, we can start to use volume, hex, and sweep, and everything. And of course, it takes a few seconds more. Okay. In this way, we have the complete model with elements and nodes, and we can plot plot, but they will be the same thing because we have element there. You see there are elements here. And we can plot nodes. Now we have nodes. Okay, we have many nodes here. Then we can list, and list is to list. It will be the same as you list the nodes here. And list, enter. Let's see how many nodes you have. You have 52,000, a bit more than 52,000. List. And pay attention, in student version of ANSYS, you have a limit of number of elements. Probably it's less than 41,000. So maybe you have to use a crosshair mesh for some specific part. Okay, eplot. Let's see. Okay, seems looks fine. So probably you can instead of 100 division for this length direction, probably you can use less there. Okay. You see, we will say we have a good element if they are closer to a square. So probably you can have a little bit more. So the aspect ratio A and B is better to be close to 1. In some case, they will say they will show in up some warning here to say some numbers out of the full number of elements are not in good shape, and pay attention to that. This is a warning. Of course, it's not that critical, so you can skip it sometimes. And but of course, it's better to not to have this kind of warnings. Okay, this is basically everything with this modeling part. Then what to do next is we can move to the solution part. We have to specify what is element type, is static, okay. The solution controls. Here we have to use large displacement static, okay. If we use default one, small displacement is not okay. The number of substeps is better to specify a large number. Again, even you specify this 1,000 substeps, but since the program, they will automatically change the steps, the time increasing. So even you have 100, probably the final result, you have less than 100, even you have 1,000 there. So there's no problem to use 1,000, or you can say 200, 500. And the other important thing is here, you have to write every substep. And advanced arc length, it depends on your choice. You can activate it or maybe not to use it in the beginning. Okay. Then we have to define the loads. That means the displacement, the boundary condition, and the pressure. So boundary condition in displacement, we applied on nodes. So now we plot and plot here. We make it to this right view, so we can zoom here. So we use a box, we select this one, okay, and feed view. They're still there, so it doesn't matter. This can be existing in the same time. So we zoom a little bit on the right part and we use a box. Okay. Then, okay. Then we say we can constrain the all degrees of freedom there. Okay. Now with fit view, we see these two end sections are constrained. If you plot element, it will be the same thing. You can see the boundary condition there. The next step is to apply the pressure. We can do it on areas, but later on, actually, the program will automatically calculate it or convert it, this load to the nodes and elements. Just for easy application, we can do, let's do a plot. So we can select now the different ways to do the selection. So I think this is the one, and we need this one. Okay. Yes, you can use you can hold on a mouse and then just move a little bit to try to select those, this one and this one. So in the middle, we need also one like that, and this small one there. Okay. If I did Okay, so we can select the area first. A plot. Maybe I click something wrong here. It's not. It should be on areas. Okay, let me try to plot all the areas. So now we can select the area first. P by peak. Is the by peak should be in the one more place. Yes, the type. You can put an S select from all, or this is default one. So if you didn't put anything, that would be fine. Peak by peak. Okay, now I will do it again. This is inner. This is second middle. So this is the outer part. Again, I do the outer part for this one. Okay, and let me try to rotate it a little bit. I will check the outer part for the yes. So now I need this one, the outer part. Like this, yes, like this. And now if you change it from front view, you will see, no, you won't see it. And I will select one more, that is this one, encroaching defect. 6 areas, okay. I always click somewhere there. So let's deactivate this one. Plot, replot, okay. If you see now in front view, you will see, okay, you have this outer circle, that's fine. And you have one arc there. That is because of the crossing part, okay, because here you have this one there. Then you may ask, what about these? What about these areas, small areas there? If there's water pressure coming like from these different, but since they are quite small, so let's say for simplicity we ignore that part. So the only area we're going to apply the external pressure is these areas being selected. Then, of course, we're going to apply pressure on areas. Now we can use pick all. Again, this pick all doesn't mean that everything you have in your model. This means everything you have been selected. So the existing all the areas. So pick all. You give a value, let's say 100 E6, okay, because I'm using SI unit, so it's in meters, the pressure is in Pascal, and if you want to megapascal, we have to times 10 to the power 6, and okay, you see red color, because of the default go to plot control symbols, the default show is phase outlines, so let's change it to arrows. Okay, so we can see in this view, okay, they're applied. And also there's one applied to the crossing area. So basically you can start to solve it. Let me think. Yes, you can solve it now. But one thing you have to do is to select everything, okay? Because we select some part. Is click select everything is the same as all S or all cell. Enter, okay. Now if you report, you will see all the areas. Yes, like this. In this case, it's okay because we have all the elements in the nodes. We didn't select part of it. But once you select partial nodes or elements, then you solve the model, there will be a big problem, there will be an error. And also, we are still showing the pressures, and the values could be seen here. Okay, pressure is this value. So next step is only to solve the current load step, okay? Then there will be a status window to show, just to say you have static, 3D, and some information. Okay, just check it and close it, and then if you click OK, then it will start to solve your model. Okay, I don't solve it at this moment because as I said, I use a random value like 10 and 9, 8 for this thickness or for the pipe. If I think this is in meters, of course, this is too strong. We don't have a thickness of like 1 meter. So in your case, of course, you will try to substitute these values by your model. But trying to show you what is the step of process, I have here another model. Yes, I think it was done by some student before in previous years. They have this mesh, which is not, okay, I can change the title. Not to see you. This is from group 5 students last year. Okay, then we plot. And this is, if you remember, this is the step 1 and 2, optional ones to change the job name, directory title, etc. So the title will appear on the screen. By the way, how you can save the image? You can go to prod controls and redirect ports and to TIFF. This is some journals that require this TIFF. Or if you want, you can simply save it to JPG or PNG. And one thing is to convert this white and black color. If you didn't tick this one, they will be saved in black color, like what we have there. Or even you do a screenshot, you will have this black background, which is if you want to publish it in a thesis or a journal paper or an international conference, it's better to have white background. I will try to do both to see what is the difference. Okay, without this one, apply, and I turn it on and okay. Then let's go to the folder we have saved. This is the one with black color, and this is the one with the white color background. And this one is recommended to be used in a report, in a formal article to be published. And of course, some like personal private information, like what time you did it, that depends on your choice. It can be there, or we can go just right click here and graphic properties, graphic options. You can if you say I don't want the title there, you can deactivate it, apply, and you see it disappear there. If you want it, okay, it becomes there. And the time and date, you can change just date, okay, not time. Apply, you see that hours disappear, but you still have it May 28th. And you don't want to any information of the date and time, apply, okay. And you see, I don't want to show the ANSYS version because I'm using the full version of 15 in this computer. So text, you still have it there. So probably legend off, apply, yeah. But not to show it. Multi-legend. Okay, probably you cannot delete this 15.1. Okay, then the original of this is your XYZ coordinate. If I say I want to show it on the bottom left, okay, it becomes here, and which is sometimes more clear. And what's on? So you can check here what you want to be there or not to be there during the plot of an image. Okay, cancel. Then if we have this model, let's check if the end plot, if the boundary is already there. Okay, it is there. And let's check the pressure. Yes, it's there. If we see it in this front view, okay, you can see it's being well applied. Plot area. You will see, yes, we have this one for the corrosion defect part. And plot. Now it's like that. So select everything. The plot. So we're going to solve it. And it's in solution. Solve the current, just to check the solution controls. Okay, large and 1000 white array substep. Okay. Then we're going to solve it. And what is the pressure that I applied? I don't remember. Loads, service on all areas. So there are 6 areas, and I applied. This is 100 megapascal. Okay. So I'm going to solve it. This one, no. Okay. Sometimes there will be warnings to verify, but the warnings are not that severe. Of course, you can go to your document folder to check this number 2 error. What is this one? Okay, just to say some mesh. Okay, as I said, the mesh style is not very satisfactory. Later on, I will see how we can improve it. The way I showed before is a good way, okay? But still, despite this warning, you can still continue to solve it. And then you see this is a 0.001, 0.002, but now it moves largely, not 3, 4, but 5 and 9, okay? You can also check the information here in this output window. So in this case, I think this model is simple and it takes just few minutes, maybe just 1 minute to complete. And again, this time could be the ratio or the percentage of the load application. I mean, if we apply 100 megapascal, now we applied increasing little by little. Now it's 38, 39, 40 megapascal, and it's still working. The pipe is still good. Okay, then it tells you your solution is done. Why it stops? Because the pipe collapses, actually, because you have set what is a material property. So the pipe fails at this time. It doesn't mean the real time. This is more or less the percentage of the load application. So you can have a conclusion in your pipe, in this pipe we're solving now, in the configuration of this pipe. The collapse pressure will be 42.3 megapascal. And this is the important conclusion we want. And of course, we can go to the post processor. Firstly, we have to read the results by peak. If you remember in this solution controls, there's an option to write array substep. And the advantage is here, you can have different time step, and you can, of course, check the results. What is deformation at this step? What is deformation at that step? Okay. And you can read the result. Oh, there is also a function of result viewer, which is also good to check the changing, let's say, the deformation, the overall deformation. So we have it like this, like that. Okay, I think the difference is not very obvious. What we can do there, we can select only the middle part, let's say E cell, pick with the box. I will just pick these elements there, okay. We plot, okay, we will have smaller one there. And we can use a scale factor, D scale, let's say 100 times. Just use a large value, just help you to see it in a better way. Okay, of course, this 100 times is too much. So let's say 20. Okay. Yeah. Okay, let's see it in the front view. So we can go to result viewer. There you can check this displacement, and then let's check in different time how it goes. Okay. So it seems okay until like around 40 megapascal the pressure, but now when it close to it approaches the maximum, the craft pressure, this is the ultimate capacity it can sustain, so it becomes large, and probably there will be a hole or a crack there for this one, even it's not quite visible. We can also check what is the stress. Okay, that depends also on the material properties, the stress strain curve. Let's check the von Mises. Okay, at this time. So this value means 562 megapascal. Okay, so since it reaches or it oversees the yield stress of the material of a pipe, of a steel, so probably the failure occurs like that. Okay, so in general, you can maybe select everything to see the whole pipe. So probably you can have a plot of the pipe like this. Let's say this is the von Mises stress, or you can have a plot, the solution of U and the sum. Okay, the displacement. What is the problem? Without this one, yes. Okay, like this. And of course, if you use scale factor, or maybe a view like this, or you can select the local part to say it more clear, it's also possible. You can, what I did is select E cell, pick some part of it, replot, rotate a little bit. Okay, or things like this. You can do this. You can include this image in a report. Okay, let's see what. That's, I think, basically everything I want to show you. Okay, by pick, first you always pick the last one. And probably you can say, what if this 100 megapascal, how I can apply the load? I mean, this will be an expansion, and then you can do it more than, you can use a value more than the collapse strength of the pipe that you obtain from the design value, or you just randomly you just estimate during your prediction. Okay, so let's say if you use 50 megapascal load application, it's also okay because it's more than 42, and then the time to stop probably will be like 0.84. Okay, it's not, maybe not exactly doubled, but the relative error is small, like 1-2% difference could be there. And let's try to delete the load, the pressure. I will use the same. I will use a different pressure. Delete structural pressure on all on all on areas. Pick all. Okay. So now if we plot the element on node, okay, the pressure is not there. So what if we apply a pressure less than 42? So the calculation will stop, we finish at 1. I mean, they will complete all the steps. Pressure on areas. Okay, but unfortunately I missed that all this area. So I have to do that again. So it would be nice if you can have you can use this component. I forgot to create a component of that areas. And that is a good way for future use. So now let me see how I can do it. I will select these areas. Trying to do it. Sometimes this kind of selection you may feel it's too difficult, and it is sometimes. So you may use different way, like you can use location, XYZ location, like what I showed in the beginning of the class. You can use, no, it's this one. You can use the cylindrical coordinate system and then trying to select the areas by the radius. Okay, I think that these are the 6. Okay, and I will say I give it 20 megapascal. So what will happen if I apply that load? Okay, I don't change it the view to errors because I know it should be correct. But it is always important to check it because I checked it before. So I can just simply solve it again. I mean, you can do it without to open a new file of ANSYS. You can just simply solve it. And what is, okay, I have to select everything. And plot, let's check the boundary condition and plot. Do we have the boundary condition? Yes, I have it. So I can solve it. Okay, I forgot to close this window. Now I cannot do that, so I didn't see this time. But we will see it when the solution is done. Alternatively, we can see it from the output window here. Okay, time is 1. Time is 0.2 here. 0.3. And I can tell you they will finish at time equals 1. And if you check, there will be deformation and there will be a stress, but the stress will be, of course, less than the yield stress of the material. So that's the idea. And basically, we have these two different types of analysis. They are both static analysis. But for this case, like what we are doing now, is like we have a certain load, like you can say from the environmental condition, the pipe or the structure is supposed to subject to this kind of loading with a fixed number. So what will be my structural response according to this loading? So I will say, and this is with what kind of information or what kind of stress. And in this case, we can get a conclusion like our pipe is safe in this kind of condition. So this is one type of analysis. The other one is we don't know what is the loading. So we use this increasing load, or let's say collapse, progressive collapse kind of analysis, trying to find out what is the ultimate limit state of the structure, or what is the, in this case, what is the collapse pressure of our pipe. Okay, you can increase, you can try use different loading, okay, to see when it fails. Okay, that's basically everything for today. I can stop the recording now.